time travel. It's one of those ideas that seems impossible, yet we can't stop thinking about it. What if you could go back and meet your younger self? What if you could skip ahead to see what the world looks like in 100 years? What if you could witness dinosaurs or watch the pyramids being built or see the end of the universe? Here's the thing though, time travel isn't just science fiction anymore. According to Einstein's theory of relativity, time travel is actually possible. Not in the way you see it in movies with DeLoreans and phone booths, but it's real. In fact, we're all time traveling right now, just very, very slowly into the future. Every second that passes, we move 1 second forward in time. Today, we're going to explore 101 mind-bending facts about time travel. We'll talk about the science behind it, the weird paradoxes it creates, the different theories about how it might work, and the wild possibilities it opens up. We'll look at what's actually possible right now, what might be possible someday with advanced technology, and what's probably impossible forever, no matter how smart we get. Fair warning, some of this is going to seriously mess with your head. Because once you really understand how time works, or more accurately, how it doesn't work the way you think it does, you'll never think about reality the same way again. But before that, please make sure to like the video and subscribe the channel. Now, let's start with the most basic question. What is time? Before we can talk about traveling through time, we need to understand what time actually is. And here's the weird part that might surprise you. Scientists still don't completely agree on that fundamental question. We use time every day. We measure it with clocks. We organize our lives around it. But when you really dig into what time is, things get strange fast. The simplest definition of time is that it's the measurement of change. Things move from one place to another. Things decay and break down. Things happen in a sequence, first this, then that, then something else. That progression, that ordering of events, that's what we call time. Without change, without things happening, there would be no meaningful concept of time at all. We experience time as a one-way street. You remember yesterday, you're living through today, and tomorrow hasn't happened yet. You can't go back to last week, you can't skip ahead to next month, and you definitely can't reverse the flow. At least, not in any normal way that we know of. Time just keeps marching forward, second after second, minute after minute, whether we like it or not. But here's where things start to get interesting. Einstein proved something absolutely revolutionary. Time isn't actually the same for everyone. This is probably the most important discovery about time ever made. Depending on how fast you're moving through space and how strong the gravity is around you, time can actually run faster or slower for you than it does for someone else. This isn't some theoretical idea or mathematical trick. It's a real, measurable phenomenon that we can detect with precise instruments. This means time is relative. There's no universal cosmic clock ticking away the same for everyone throughout the universe. Your time is your time, my time is my time, and someone in a different situation might experience time flowing at a completely different rate. Two people can start their stopwatches at the same moment, go off and do different things, come back together, and their stopwatches will show different amounts of time has passed. That seems impossible, but it's absolutely true. Here's the really mind-bending part. The faster you move through space, the slower you move through time. This is called time dilation, and it's not just a theory someone made up, it's a proven fact that we've tested over and over again. If you could somehow get on a spaceship and travel at nearly the speed of light, time would slow down for you compared to people back on Earth. From your perspective, everything would seem normal. But when you came back, you'd find that much more time had passed on Earth than passed for you. Let me give you a real-world example of this. GPS satellites have to account for time dilation just to work properly. These satellites are moving fast, about 8,700 miles per hour, and they're in orbit where gravity is slightly weaker than it is on Earth's surface. Both of these factors affect how time flows for them. If GPS satellites didn't correct for the fact that time runs slightly differently for them than it does for us on the ground, your GPS navigation would be off by several miles within just a single day. Think about that. Your phone has to account for time travel effects just to tell you where you are. Now, here's something even weirder. Some physicists think time might not even be a fundamental part of the universe at all. It might be what's called an emergent property, something that appears to exist, but is actually created by something more fundamental. One idea is that time is an illusion created by entropy. Entropy is the tendency of things to move from organized states to disorganized states. A cup falls off a table and shatters. That's entropy increasing. And some physicists think our sensation of time moving forward is just us experiencing this increase in entropy. The universe is moving from order to disorder, and we perceive that as time flowing. Here's another strange thing about time. According to the fundamental laws of physics, the equations that describe how particles and energy behave, there's nothing that says time has to flow forward. You can take almost any physics equation and run it backward in time, and it still works perfectly. The math doesn't care which direction time flows. If you filmed a bunch of billiard balls bouncing around on a table and played the video backward, the physics would still make sense. The balls would follow the same laws whether time is running forward or backward. Yet we only ever experience time moving in one direction. We remember the past, but not the future. We see cups shatter, but we never see them spontaneously reassemble. We get older, never younger. Entropy always increases, never decreases. This is called the arrow of time, and why it points in only one direction is genuinely one of the biggest unsolved mysteries in all of physics. We don't know why time has a direction. We just know that it does. Okay, so here's the good news about time travel. Forward time travel is absolutely 100% possible. It's not science fiction, it's not speculation, it's real, proven, and we've actually done it. In fact, you're doing it right now as you watch this video. You're traveling into the future at a rate of 1 second per second. But we can do better than that. Every time you move, you're actually time traveling into the future faster than someone who's standing still. The difference is incredibly tiny. We're talking fractions of a nanosecond, but it's real. The faster you move, the more you time travel. This is the same time dilation effect we talked about earlier, and it's been proven beyond any doubt. Let's talk about a real example. Astronauts on the International Space Station are time traveling into the future right now. The ISS orbits Earth at about 17,500 miles per hour. That's incredibly fast by everyday standards, about 5 miles per second. Because they're moving at this speed, time runs slightly slower for them than it does for us on the ground. Not by much, but by a measurable amount. Here's a specific example. There was a Russian cosmonaut named Sergei Krikalev who holds the record for most time spent in space, 803 days in total across multiple missions. Because of all that time spent moving at high speed in orbit, time moved slower for him than for people on Earth. By the time he returned, he had time traveled about 0.02 seconds into the future. That means he's effectively 0.02 seconds younger than he would have been if he'd stayed on Earth the whole time. Now, 0.02 seconds doesn't sound like much, and it isn't, but it proves the principle. It shows that time travel to the future is real and actually happens. If we could just speed things up, literally, we could time travel much farther. Let me give you some numbers that'll blow your mind. If you could somehow build a spaceship that could travel at 99.9 the speed of light, and you took a trip in that ship for 1 year from your perspective, when you returned to Earth, you'd find that about 22 years had passed here. You'd have time traveled 21 years into the future. Your family and friends would be 2 decades older, but you'd only be 1 year older. And it gets even more extreme. If you could push that speed up to 99.99, the speed of light just a tiny bit faster, 1 year of travel for you would equal about 70 years passing on Earth. You'd come back to find your children elderly or gone, your world completely changed, all while you'd experienced only 12 months. The closer you get to the speed of light, the more extreme this time dilation effect becomes. At exactly the speed of light, if you could reach it, which you can't because matter with mass can never quite get there, time would stop completely for you from the perspective of outside observers. A journey that took the entire lifetime of the universe from Earth's perspective would feel instantaneous to you. Now, there's another way to time travel to the future besides speed, and that's gravity. The stronger the gravity you're experiencing, the slower time runs for you. This means time actually runs slightly faster on top of a mountain than it does at sea level, because there's slightly less gravity up high. The difference is minuscule. We're talking billionths of a second, but it's real and measurable with atomic clocks. But what if we ramp up the gravity? Near a black hole, time dilation becomes absolutely extreme. A black hole warps space-time so severely that time behaves in completely bizarre ways around it. If you could somehow position yourself in orbit close to a black hole's event horizon, the point of no return, and spend just a few hours there, when you return to Earth, you might find that centuries or even thousands of years had passed. The movie Interstellar actually got this right, which is impressive for a Hollywood film. There's a scene where the crew lands on a planet near a massive black hole. Because of how close they are to the black hole, time dilation is extreme. They spend a few hours on the planet's surface, and when they return to their ship, the crew member who stayed behind has aged 23 years. 1 hour on that planet equals 7 years back home. The math in that movie was actually done by physicist Kip Thorne, and it's accurate. So theoretically, if we could build a spacecraft that could get close to a black hole and return safely, we could send people thousands or even millions of years into the future. They'd experience just a short trip, but they'd emerge in a completely different era of human history or beyond human history entirely. Here's the important thing to understand. Forward time travel doesn't violate any laws of physics. It's weird and counterintuitive, but it's allowed. The universe has no problem with it. Time dilation is a natural consequence of how space-time works. The catch, of course, is that forward time travel is a one-way trip. Once you've traveled into the future, there's no way back. You can't reverse time dilation. If you go forward 1,000 years, you're stuck there. Everyone and everything you knew is gone. That's a pretty big downside. The other big problem right now is practical. We don't have the technology to accelerate something to anywhere near the speed of light. The amount of energy required is absolutely staggering more energy than all of human civilization produces. We also don't have the technology to safely approach a black hole and return. So while forward time travel is definitely possible in principle, actually doing it in any meaningful way is still far beyond our current capabilities. But the important point is, it's not impossible. It's not forbidden by the laws of physics. If we figure out the technology, we could do it. Now we get to the really tricky part. Backward time travel. Going back to the past. This is what most people think of when they imagine time travel, and it's where physics gets really strange and where scientists start arguing with each other. Here's the current state of things. Most physicists think backward time travel is probably impossible, but we can't definitively prove it's impossible. Einstein's equations, the ones that describe how space-time works, don't actually forbid backward time travel. They just make it really, really hard. Like, you'd need to manipulate the fabric of reality itself hard. Let me explain the main theoretical ways someone might travel backward in time, and why each one is so difficult. The first possibility is something called a wormhole. Imagine space-time as a flat sheet of paper. Normally, if you want to go from one point on the paper to another, you'd travel across the surface. But what if you could fold the paper so the 2 points touch, then poke a hole through both points? Now you have a shortcut, a tunnel through the paper. That's basically what a wormhole is. A tunnel through space-time that connects two different points in space and potentially in time. If wormholes exist, and if you could manipulate one end of the wormhole in just the right way, you might be able to turn it into a time machine. Here's how it would work. You take one end of the wormhole and accelerate it to near light speed, then bring it back. Because of time dilation, less time would have passed for that end of the wormhole than for the stationary end. Now the two ends are connected but exist at different times. Step through one end, and you emerge at an earlier time at the other end. Boom, you've traveled to the past. But there are massive problems with this idea. First, we've never actually seen a wormhole. We don't know if they exist. They're allowed by Einstein's equations, but that doesn't mean they actually exist in nature. It's like how the equations allow for perpetual motion machines mathematically, but the real world doesn't. Second, even if wormholes do exist naturally somewhere in the universe, they'd almost certainly be unstable. Any small disturbance like, say, trying to send something through them would cause them to collapse immediately. You'd need some way to stabilize them and keep them open. And that brings us to the third problem. To keep a wormhole open, you'd need something called negative energy or exotic matter. This is matter with properties we've never observed. Normal matter has positive energy density. It attracts other matter through gravity. Exotic matter would have negative energy density. It would repel normal matter and create negative gravity. We've never detected anything like this, and we're not sure it can even exist. Some physicists have argued that quantum effects might allow for tiny amounts of negative energy in very specific circumstances. But scaling that up to keep a wormhole open? That's a whole different challenge. And even if exotic matter exists and we could produce it, we'd need enormous quantities of it, maybe more mass than exists in several stars. That's not exactly practical. Here's another theoretical method: the Tipler cylinder. This was proposed by physicist Frank Tipler back in 1974. The idea is that if you had a massive cylinder, and I mean massive, like made from the mass of multiple stars, and you set it spinning at nearly the speed of light, the rotation would drag space-time around it. If you flew a spaceship around the cylinder in just the right path, you could theoretically arrive at a point in your past. The math actually works out. The problem? The cylinder would need to be infinitely long. Yes, infinitely long. Not just really long, actually infinite. That's obviously not possible. So while the Tipler cylinder is interesting theoretically, nobody thinks it's a practical method for time travel. There's also something called a Gödel universe, named after the mathematician Kurt Gödel. He showed that if the universe as a whole is rotating in a specific way, then paths through space-time that loop back on themselves would be possible. You could literally take a trip through space and end up back at a point in your own past. Sounds great, right? Problem: our universe doesn't appear to be rotating in the way required for this to work. So while it's theoretically possible in some universes, it doesn't seem to apply to ours. Then there are cosmic strings. These are theoretical one-dimensional defects in space-time, kind of like cracks that might have formed in the very early universe as it cooled down, similar to how cracks form in ice. If cosmic strings exist, and if you could find two of them moving past each other at nearly the speed of light, you might be able to use their combined gravitational effects to create closed loops in time. But again, we've never found a cosmic string. They might not exist. And even if they do, finding two moving past each other at the right speed, good luck with that. The most famous theoretical time machine was actually proposed by physicist Kip Thorne, the same guy who did the physics for Interstellar. His idea involves a wormhole and some very careful manipulation using exotic matter and precise calculations. It's probably the most serious scientific proposal for a time machine that's ever been published. But even Thorne admits it requires exotic matter we don't have and technology far beyond anything we can currently imagine. Stephen Hawking looked at all these possibilities and proposed something called the chronology protection conjecture. Basically, his argument was that the laws of physics seem to be set up in such a way that backward time travel is prevented. Every time someone figures out a theoretical way that time travel might work, there's always some physical principle that steps in and prevents it from actually functioning. Hawking's point was that maybe the universe doesn't like time travel because it creates paradoxes, and the universe really doesn't like paradoxes. Maybe there's some fundamental law we haven't discovered yet that specifically prevents backward time travel from being possible. One piece of evidence for this is what you might call the "where are the time travelers" problem. If backward time travel is possible and will ever be invented, then we should see time travelers from the future visiting our time. But we don't see any obvious time travelers. That might mean time travel is never invented. Or it might mean time travelers are really good at hiding. Or it might mean you can only travel back to the point when the time machine was first created, so there won't be any time travelers visiting us until after we build one. The bottom line is this: backward time travel is nowhere near as simple or straightforward as forward time travel. It might be impossible. It might be possible, but require technology so advanced that we'll never achieve it. Or it might be possible, and someone in the future will figure it out. We simply don't know yet. Now, let's talk about why backward time travel creates such enormous problems, paradoxes. These are logical contradictions that seem impossible to resolve, and they're one of the main reasons many physicists think backward time travel probably can't happen. The most famous time travel paradox is called the grandfather paradox, and it goes like this. Imagine you build a time machine and travel back to a time before your parents were born. You find your grandfather as a young man, and for whatever reason, maybe it's an accident, you prevent him from meeting your grandmother. Maybe you distract him at a critical moment, or you convince him to move to a different city, or in the most extreme version, you actually kill him. Now, here's the problem. If your grandfather never meets your grandmother, your parents are never born. And if your parents are never born, you're never born. But if you're never born, then you can't travel back in time to prevent your grandfather from meeting your grandmother. So he does meet her, your parents are born, you are born, and you do travel back in time to stop them from meeting. But that means you're never born, which means you don't travel back, which means they do meet, and around in a circle. It's a logical contradiction. The event both happens and doesn't happen. You both exist and don't exist. The universe can't be in two contradictory states at once. So what gives? There are several proposed solutions to this paradox, and each one has interesting implications. The first solution is the self-consistency principle, sometimes called the Novikov self-consistency principle, after physicist Igor Novikov. This says that anything a time traveler does in the past must have already been part of history. In other words, you can't change the past because anything you do in the past was always part of what happened. Under this principle, if you try to kill your grandfather, something will always prevent you from succeeding. Maybe your gun jams, maybe you trip at the critical moment, maybe someone intervenes, maybe you just lose your nerve. Whatever it is, the universe will conspire to prevent you from creating a paradox. You have free will to try whatever you want, but the outcome will always be consistent with the history that already happened. This leads to interesting scenarios. Maybe you travel back in time planning to kill your grandfather, but instead, your actions cause your grandparents to meet. Maybe you're actually the reason they got together in the first place. History is consistent because your time travel was always part of it. The second solution is the many worlds interpretation, which comes from quantum mechanics. This suggests that when you travel back in time, you don't actually go back to your own past. Instead, you create a branching timeline, a parallel universe. In this new timeline, you can do whatever you want, including killing your grandfather, because it's not really your grandfather. It's the grandfather from this alternate timeline. In this scenario, when you prevent your grandparents from meeting, you're not preventing your own birth in your original timeline. You still exist in your timeline. You've just prevented the birth of an alternate version of you in this new timeline. No paradox, because you're not actually changing your own past, you're creating an alternate past. This solution is appealing because it allows for backward time travel without logical contradictions. But it raises other questions. Where do these parallel timelines come from? Do they exist already, or does time travel create them? And if you travel to a parallel timeline, can you ever get back to your original timeline? These are unanswered questions. There's another famous paradox called the bootstrap paradox, sometimes called the ontological paradox. This one is weird in a different way. It goes like this. Imagine you're a huge fan of Shakespeare. You have a complete collection of all his works. One day you build a time machine and decide to travel back to meet him. You arrive in Elizabethan England and track down Shakespeare. But you discover that he's just a struggling playwright who hasn't written his famous works yet. So you think, I'll give him a little help. You hand him your complete works of Shakespeare and say, here, you can use these. Shakespeare copies them and publishes them as his own. The plays become famous. Centuries later, your copy of these plays exists. You take them back in time and give them to Shakespeare. Here's the question: who actually wrote the plays? Shakespeare copied them from you, but you got them from published editions that Shakespeare had copied from you. The information exists in a loop with no origin point. The plays were never actually created by anyone. They just exist, looping through time. Where did they come from originally? The paradox is that they have no cause, no beginning. This bootstrap paradox applies to objects and information. It creates things that exist without ever being created, which seems to violate basic logic and possibly the laws of thermodynamics. Then there's the predestination paradox. This is when a time traveler goes back in time to prevent something from happening, but their actions actually cause the very thing they were trying to prevent. It's the ultimate self-fulfilling prophecy. A classic example is from a short story called All You Zombies by Robert Heinlein. In it, a time traveler goes back and accidentally becomes their own grandfather and grandmother through a series of time travel loops. The story is mind-bending, but the point is that the time traveler's existence is only possible because they went back in time, creating a causal loop where they are their own ancestor. Movies like 12 Monkeys and Predestination are based on this idea. The protagonist tries to prevent a disaster, but it turns out their attempts to prevent it are what causes it in the first place. The timeline is fixed and self-consistent, but in a really twisted way. Some physicists argue that these paradoxes are proof that backward time travel is impossible. If the universe doesn't allow logical contradictions, and backward time travel creates logical contradictions, then the universe won't allow backward time travel. It's that simple. But others argue that paradoxes aren't proof of impossibility, they're just puzzles we need to solve. The self-consistency principle shows that you might be able to have time travel without paradoxes if events always work out in a self-consistent way. The many worlds interpretation shows that you might avoid paradoxes by having time travel create parallel timelines. There's also a principle from quantum mechanics called the Novikov self-consistency principle. which mathematically shows that if an event would create a paradox, the probability of that event is 0. It's not that something stops you from creating a paradox. It's that the configuration of events that would lead to a paradox simply doesn't happen. The universe's probability waves arrange themselves in such a way that paradoxes are automatically avoided. Here's a simpler way to think about it. Imagine you're trying to shoot your past self, but your past self is you. If you succeed, you die, which means you never lived to become the future you who went back in time to shoot your past self. Under the self-consistency principle, this means something will always prevent the shot from being fatal. Maybe you miss. Maybe the gun jams. Maybe your aim is off just enough that it's only a flesh wound. Whatever happens, the outcome will be consistent with the fact that you survived to become your future self. The question of paradoxes remains one of the most fascinating and frustrating aspects of time travel theory. They might prove time travel is impossible, or they might just show us that time travel would work in ways we don't expect. Everything we know about the possibility of time travel comes from Albert Einstein's theory of relativity. This is probably the most important discovery in physics in the last 200 years, and it completely changed our understanding of time, space, and reality itself. Before Einstein came along in the early 1900s, everyone, including physicists, thought time was absolute. They thought there was one universal time that flowed at the same rate for everyone, everywhere in the universe. If it was noon in New York, it was some specific time everywhere else, and everyone would agree on how much time had passed between events. Time was thought to be completely separate from space. You had 3 dimensions of space and 1 dimension of time, and they didn't interact with each other. Einstein proved that was totally wrong. In 1905, he published his special theory of relativity, which dealt with objects moving at constant speeds. In 1915, he published his general theory of relativity, which extended the ideas to include acceleration and gravity. Together, these theories revolutionized physics. Special relativity showed that time and space aren't separate. They're woven together into a single 4-dimensional fabric called space-time. You can't affect one without affecting the other. When you move through space, you're also moving through time. And the faster you move through space, the slower you move through time. This is where time dilation comes from. The key insight is that the speed of light is constant for everyone, no matter how fast they're moving. This seems simple, but it has profound implications. If you're on a train moving at 60 miles per hour and you throw a ball forward at 20 miles per hour, the ball's moving at 80 miles per hour relative to the ground. That's how speeds normally add up. But light doesn't work that way. If you're on a spaceship moving at half the speed of light and you shine a flashlight forward, the light doesn't travel at 1.5 times the speed of light. It travels at exactly the speed of light, same as always. This is true no matter how fast you're going. For this to work, time and space have to be flexible. They have to adjust themselves so that light always moves at the same speed from everyone's perspective. And that means time must flow at different rates for people moving at different speeds. There's a famous thought experiment called the twin paradox that illustrates this. Imagine you have identical twins. One stays on Earth and the other gets on a spaceship that accelerates to nearly the speed of light, travels to a distant star, and comes back. When the traveling twin returns, they'll find that they're now younger than their sibling who stayed home. This isn't just a thought experiment anymore. We've effectively tested this with atomic clocks on airplanes, and it works exactly as predicted. Here's what happened. Both twins aged normally from their own perspective. The traveling twin didn't feel time moving slower, but because they were moving so fast relative to Earth, time actually did move slower for them compared to their Earthbound sibling. Less time passed for the traveling twin than for the stay-at-home twin. The traveling twin experienced, let's say, 5 years of journey, but 40 years passed on Earth. They're now 35 years younger than their twin. This has been tested in real experiments. Scientists put atomic clocks, incredibly precise timekeeping devices, on airplanes and flew them around the world. They compared these clocks to identical clocks that stayed on the ground. When the planes landed, the flying clocks showed less time had passed than the ground clocks. The difference was tiny, just a few hundred nanoseconds, but it was exactly what relativity predicted. Now let's talk about general relativity, which deals with gravity. Einstein showed that gravity isn't really a force pulling objects together. Instead, massive objects like planets and stars actually warp the fabric of space-time itself. Imagine space-time as a stretched rubber sheet. If you put a heavy ball on the sheet, it creates a depression. Other objects rolling nearby will curve toward the depression. That's gravity. The warping of space-time affects both space and time. Near massive objects, time runs slower. This means time flows more slowly at sea level than on top of a mountain, because sea level is deeper in Earth's gravitational well. The difference is incredibly small, but it's real and measurable. Near extremely massive objects, this effect becomes much more pronounced. Near a black hole, time dilation becomes extreme. At the event horizon, the point of no return around a black hole time dilation becomes infinite from the perspective of an outside observer. If you watch someone falling into a black hole, you'd see them slow down and appear to freeze right at the event horizon, even though, from their perspective, they'd fall right through. Black holes create such extreme warps in space-time that they trap light. At the event horizon, the warping becomes so severe that all paths through space-time lead inward. There's literally no way out, not even for light traveling at maximum speed. Inside the event horizon, the roles of space and time actually switch. The direction toward the center of the black hole becomes more like forward in time than forward in space. Falling into the center becomes as inevitable as moving forward in time normally is. Here's something else interesting. From your perspective, falling into a black hole, time would seem to flow normally. You wouldn't feel like time was slowing down, but you'd see something strange looking outward. Because of time dilation, you'd see the entire future of the universe flash by. You'd watch stars being born and dying, galaxies colliding, possibly even the eventual heat death of the universe, all compressed into what might feel like moments to you. This means black holes are, in a sense, one-way portals to the far future. If you could somehow survive getting close to one and then escaping, which is probably impossible, you could emerge millions or billions of years in the future. Space and time being woven together into space-time means that time is just another dimension, like a length, width, and height. We can move freely in the 3 spatial dimensions, but we seem stuck moving in only one direction through time. Why? Nobody knows for sure. It's one of the deep mysteries of physics. The fact that relativity allows for time dilation and that time dilation means time travel to the future is possible is one of the most profound discoveries in science. It means time travel isn't just science fiction, it's a real feature of how the universe works. So far, we've talked about relativity and how it allows for time travel, but there's another branch of physics that might have something to say about time travel: quantum mechanics. This is the physics of the very small atoms, electrons, photons, and even smaller particles. And at that scale, things get really weird. Quantum mechanics has its own strange relationship with time that's completely different from relativity. In the quantum world, particles don't have definite properties until you measure them. Before measurement, a particle exists in what's called a superposition. It's in multiple states at once. An electron might be spinning clockwise and counterclockwise simultaneously. A photon might be in multiple places at once. It's only when you observe the particle that it decides which state to be in. This is famously illustrated by Schrödinger's cat, a thought experiment where a cat in a box is both alive and dead until you open the box and look. It sounds absurd, and it is absurd, but that's genuinely how quantum particles behave. They exist in multiple states simultaneously until observed. Now, here's where it connects to time travel. Some interpretations of quantum mechanics suggest that particles can, in a sense, be influenced by the future. There's a phenomenon called quantum retrocausality, where the state of a particle now might be influenced by what happens to it in the future. It's like the particle knows what's going to happen to it and adjusts its current state accordingly. This doesn't mean information is traveling backward in time in any useful way we could exploit. It's more subtle than that. But it suggests that at the quantum level, time might not flow strictly from past to future the way it does in our everyday experience. There's also something called quantum tunneling that involves particles apparently borrowing energy from the future. Here's how it works. Imagine a particle that doesn't have enough energy to climb over a barrier. In classical physics, it just can't get over, it's stuck. But in quantum mechanics, the particle can sometimes appear on the other side of the barrier, as if it tunneled through. One way to explain this is that the particle briefly borrows energy from the vacuum of space, uses that energy to get over the barrier, and then pays it back. This happens so quickly that it doesn't violate conservation of energy. But where does the borrowed energy come from? Some interpretations suggest it comes from the future. The particle is essentially taking energy it will have later and using it now. Again, this doesn't mean we can build a time machine from quantum tunneling, but it shows that at the quantum level, cause and effect might not be as straightforward as we think. In 2017, scientists in Australia did an experiment where they measured quantum particles in a way that suggested information appeared to travel backward in time. They used a setup where measuring a particle now seemed to affect what that particle did in the past. The experiment was controversial, and the results are still debated. But it hints at the possibility that quantum mechanics might allow for some form of backward causation. There's also the concept of closed time-like curves in quantum mechanics. We talked earlier about closed time-like curves in general relativity paths through spacetime that loop back on themselves. Some physicists have explored whether quantum mechanics might allow particles to travel these closed time-like curves, even if larger objects can't. The math gets really complicated here, but the basic idea is that a quantum particle might be able to go back in time and interact with its past self without creating paradoxes. This is because quantum particles can exist in superposition. They can be in multiple states at once. A particle that travels back in time might interfere with itself in its past, but in a way that's consistent with quantum mechanics. David Deutsch, a physicist at Oxford, has done a lot of work on this. He's shown that quantum mechanics might allow for consistent time travel without paradoxes, at least for particles. The trick is that quantum mechanics is probabilistic, not deterministic. A particle doesn't have a single definite path through time, it has a probability distribution of possible paths. When you add in time travel, these probabilities adjust themselves to avoid paradoxes automatically. It's kind of like the Novikov self-consistency principle we talked about earlier, but at a quantum level. The probabilities of events arrange themselves so that paradoxes never actually occur. Now, the big caveat here is that all of this applies to quantum particles, tiny things like photons and electrons. Whether it could ever apply to something as large as a person is completely unknown. The laws of quantum mechanics tend to average out at larger scales, giving us the predictable world of classical physics we're used to. It's unclear whether quantum time travel effects could ever scale up to macroscopic objects. There's also the many worlds interpretation of quantum mechanics, which we touched on earlier. This is the idea that every time a quantum event has multiple possible outcomes, the universe splits into separate timelines, one for each outcome. In one timeline, the electron spins up. In another, it spins down. Both timelines are equally real. If many worlds is correct, there might be literally infinite parallel timelines, each representing a different possible history of the universe. And if that's true, then maybe time travel between these timelines is possible, even if time travel within a single timeline isn't. Think about it this way. Instead of going back in time in your own timeline, you might be able to jump to a parallel timeline that's at an earlier point in its history. From your perspective, you've traveled to the past, but technically you're just in a different timeline. This would avoid paradoxes because you're not changing your own past, you're in a completely different universe's past. But we have no evidence that parallel timelines actually exist. The many worlds interpretation is philosophically interesting and mathematically elegant, but we have no way to test it. We can't see these other timelines or travel to them, at least not with any technology we currently have or can imagine. The connection between quantum mechanics and time travel is still very much a frontier of theoretical physics. There are ideas and mathematical frameworks, but no clear answers. What we can say is that the quantum world behaves in ways that challenge our everyday understanding of cause and effect, and that might, possibly, have implications for time travel. But whether those implications will ever lead to practical time travel is completely unknown. While we can't build a DeLorean time machine yet, there are ways we're already manipulating time in the real world. Some of these effects are tiny, but they're real and measurable. We've already talked about astronauts time traveling by tiny fractions of seconds due to their high orbital speed. But let's talk about some other real examples. Particle accelerators like the Large Hadron Collider at CERN accelerate subatomic particles to incredible speeds, 99.9999999, the speed of light or even faster. At these speeds, time dilation becomes extreme for the particles. From our perspective, these particles live much longer than they should because time is running slower for them. Let me give you a specific example. There's a particle called a muon that's created when cosmic rays from space hit the upper atmosphere. Muons are unstable. They decay very quickly. At rest, a muon typically lives for only about 2.2 microseconds. That's 2.2 millionths of a second. That's not enough time for a muon created high in the atmosphere to reach the ground before decaying. Except muons do reach the ground. We detect them all the time. How is this possible? Time dilation. The muons are moving at nearly the speed of light as they fall through the atmosphere. From our perspective on the ground, time is running slower for the muons, so they live longer before decaying. They experience 2.2 microseconds, but from our perspective, they exist for much longer, long enough to reach the ground. This is direct observable proof that time dilation is real. Without it, we wouldn't detect muons at ground level. With it, we detect them constantly. Atomic clocks are so precise that they can actually detect time dilation from very small differences in speed or gravity. In one famous experiment, scientists put atomic clocks on different floors of a tall building. The clocks on higher floors ran slightly faster than the clocks on lower floors because gravity is slightly weaker higher up. The difference was only about 90 nanoseconds over the course of a year, but it was measurable and exactly what relativity predicts. In another experiment, scientists put atomic clocks on commercial airplanes and flew them around the world. When they compared these clocks to identical clocks that stayed on the ground, the flying clocks had lost a few hundred nanoseconds. Again, this matched the predictions of relativity perfectly. These aren't just interesting experiments. Time dilation has practical applications. GPS satellites, which we rely on for navigation, have to account for time dilation to work properly. The satellites are moving at about 8,700 miles per hour and are about 12,500 miles above Earth's surface. Both factors affect how time flows for them. Because they're moving fast, special relativity says time should run about 7 microseconds slower per day for them than for us on the ground. But because they're farther from Earth's gravitational field, general relativity says time should run about 45 microseconds faster per day for them than for us. When you combine these effects, time runs about 38 microseconds faster per day on the satellites than on Earth. That might not sound like much, but GPS works by precisely measuring the time it takes for signals to travel from satellites to your receiver. Light travels about 1 foot every nanosecond, so a 38 microsecond difference means an error of about 38,000 feet, more than 7 miles. If GPS satellites didn't correct for relativity, your GPS would be off by miles within just 1 day. The fact that your phone can tell you exactly where you are on Earth is proof that relativity is correct and the time dilation is real. Every time you use GPS, you're depending on our understanding of time travel effects. Now let's talk about cryogenic freezing, sometimes called cryonics. This is a bit different from time travel, but it's often discussed in similar terms. The idea is that if you could freeze a person in a way that preserves their body and brain and then revive them later, they'd effectively travel to the future. They'd be asleep for however long, and when they wake up, they're in a future time. We can already do this with simple organisms. Tardigrades, also called water bears, are microscopic animals that can survive being frozen solid. You can freeze them, leave them frozen for years, thaw them out, and they come back to life. It's not quite the same as time travel, but from the tardigrade's perspective, it skipped over all that frozen time. We can also freeze and revive certain types of cells and even some organs for short periods. But whole human bodies? That's still science fiction. The problem is ice crystals. When you freeze living tissue, water in the cells forms ice crystals, and these crystals puncture cell membranes and destroy the delicate structures inside cells. By the time you thaw the tissue, it's been shredded at a microscopic level. Some companies offer cryonic preservation services. When you die, they freeze your body, or sometimes just your head, in liquid nitrogen, keeping you at about 320 degrees Fahrenheit. The hope is that future technology will be able to revive you and cure whatever killed you. It's a long shot. We have no idea if this will ever be possible, but some people think it's worth trying. From a time travel perspective, if cryonics ever works, it would be a form of one-way travel to the future. You go to sleep in 2024 and wake up in 2124 or 2524 or whenever technology advances enough to revive you. But it's not really time travel in the physics sense. You're not warping space-time. You're just suspended, not experiencing time while time continues around you. The longest anyone has been in a medical state of suspended animation and survived is only about an hour or so, during certain emergency surgical procedures where doctors cool the body to preserve organs. Multi-year or century-long suspension is still way beyond our capabilities. So while we have real examples of tiny amounts of time travel, and while we can theoretically freeze organisms, practical time travel of the kind we see in movies going years or centuries into the future or past is still beyond what we can actually do. Okay, so let's get practical. Could we actually build a working time machine? What would it take? What are the challenges? Let's break this down for both forward and backward time travel. For forward time travel, the technology is straightforward in principle. You need speed or gravity. The faster you go, or the closer you get to a massive object like a black hole, the more you time travel into the future. The problem is achieving the speeds or getting to the gravitational fields required. To get significant forward time travel, let's say jumping decades or centuries into the future, you'd need to accelerate a spacecraft to a significant fraction of the speed of light, let's say 90 of light speed, to make the effect really noticeable. At that speed, about 10 years would pass on Earth for every year you experience in the ship. So what's the problem? Energy. The faster you go, the more energy you need, and the energy requirements grow exponentially as you approach light speed. To accelerate even a small spacecraft, let's say just 1,000 kilograms, which is tiny by spacecraft standards, to 90 of light speed would require about 40 million trillion joules of energy. To put that in perspective, that's roughly equivalent to 10,000 nuclear weapons worth of energy. And that's just for a tiny probe. A spacecraft large enough to carry people would require vastly more energy. We're talking about energy outputs that exceed what all of human civilization produces in a year. Even if we solved the energy problem, there are other challenges. At near light speeds, even tiny particles like hydrogen atoms in space would hit your ship with enormous energy. A single proton impact at 90 light speed would release as much energy as a bullet. Space isn't completely empty. There are stray hydrogen atoms everywhere. At high speeds, this interstellar medium becomes deadly radiation that would destroy your ship and kill anyone inside. You'd need shielding, and that shielding would need to be strong enough to withstand what amounts to constant nuclear bombardment. The faster you go, the worse this problem becomes. At 99 light speed or higher, the radiation becomes so intense that no known material could protect you. Then there's the problem of acceleration. Humans can only withstand so much force. If you accelerate too quickly, the g-forces will kill you. Even at a relatively gentle acceleration of 1g, the same as Earth's gravity, it would take about a year to reach 90 of light speed. That's a very long time to be accelerating, requiring enormous amounts of fuel or some other propulsion method. Some theoretical propulsion systems might work. An antimatter engine, where matter and antimatter annihilate to release enormous energy, could theoretically provide the power needed. But we can barely produce any antimatter at all, and storing it is extremely difficult because it instantly destroys any normal matter it touches. Another idea is a Bussard ramjet, which would scoop up hydrogen from space and use it as fuel. But this only works at high speeds where you're moving through space fast enough to scoop up significant amounts of hydrogen. It can't help you get up to speed in the first place. There are also ideas about warping space itself, like the Alcubierre drive. This would create a bubble of spacetime around your ship, contracting space in front of you and expanding it behind you. You'd ride this wave of warped space, possibly faster than light relative to the space outside the bubble, while staying stationary inside the bubble. This would avoid many of the problems with conventional high-speed travel. But it requires exotic matter with negative energy, which we don't have and aren't sure exists. For gravity-based forward time travel using black holes, the challenges are different but equally daunting. Black holes exist naturally, so we don't have to create one. We just have to get to one. The nearest known black hole is about 1,500 light-years away. Even traveling at a significant fraction of light speed, which we can't do, it would take thousands of years to get there. And getting close enough to a black hole to experience significant time dilation is incredibly dangerous. You'd need to orbit just outside the event horizon, where tidal forces would try to rip your spacecraft apart. The difference in gravitational pull between the front and back of your ship would be enormous. You'd need a large black hole. Bigger ones have gentler tidal forces near their event horizons and extremely precise control to stay in orbit without falling in. If you managed all of this, spent a few hours near the black hole, and then escaped back to normal space, you might emerge centuries or millennia in the future. But it's a one-way trip, And getting there in the first place is beyond our current technology by a huge margin. Now let's talk about backward time travel. This is where things get even more complicated. If wormholes exist, we'd first need to find one or create one. Creating a wormhole from scratch would require manipulating space-time itself at a fundamental level. We have no idea how to do that. It would probably require energy densities comparable to those that existed right after the Big Bang. We're talking about energies that don't exist anywhere in the current universe, except maybe inside black holes. If we found a naturally occurring wormhole, we'd need to stabilize it. This requires exotic matter with negative energy, which we've never observed and don't know how to create. Some theories suggest that quantum effects might allow for tiny amounts of negative energy, but scaling that up to keep a wormhole open would require amounts of exotic matter comparable to the mass of a planet or star. Even if we had the exotic matter, we'd need to manipulate one end of the wormhole, probably by accelerating it to near light speed to create a time difference between the two ends. This brings back all the energy problems we talked about with forward time travel. And here's a fundamental limitation. Even if all of this worked, you could only travel back to the moment when the time machine was created. You couldn't go back further than that. So if we build a wormhole time machine in 2025, nobody could use it to visit any time before 2025. This might explain why we don't see time travelers from the future. The time machine hasn't been built yet. For other methods like Tipler cylinders or cosmic strings, the challenges are similar or worse. You'd need to manipulate objects with stellar masses, move them at near light speeds, or find naturally occurring phenomena that we've never actually observed. None of this is anywhere close to practical with current or foreseeable technology. Stephen Hawking once proposed a practical test for time travel. He held a party for time travelers on June 28, 2009. But here's the clever part. He didn't send out the invitations until after the party was over. His idea was that if time travel is possible, time travelers from the future would know about the party and come back to attend it. He waited at the party venue. Nobody showed up. Hawking took this as tongue-in-cheek evidence that time travel is probably impossible, or at least that time travelers don't want to attend physics professors' parties. But really, it doesn't prove anything. Maybe you can only travel back to when the time machine was built. Maybe time travelers have a strict policy of not interfering with the past. Maybe they did attend but stayed invisible. Or maybe time travel really is impossible. The bottom line is this: forward time travel is absolutely possible in principle, but requires technology far beyond what we currently have. Backward time travel might be possible, might be impossible, and would require technology so advanced that it's essentially magic by our current understanding. We're talking about manipulating the fabric of space-time itself, harnessing energies comparable to stars, and possibly using forms of matter that might not even exist. Could we ever develop this technology? Maybe. Thousands of years from now, or millions of years from now, if humanity or our descendants continue advancing, we might figure it out. Or we might discover that there are fundamental limits that make certain kinds of time travel impossible, no matter how advanced we become. For now, time travel remains mostly theoretical. We understand enough physics to know that certain kinds are possible, but actually building a machine that could send a person through time forward or backward is still science fiction. So there you have it. 101 facts about time travel, from the basics of what time is to the weird paradoxes, from Einstein's relativity to quantum mechanics, from practical examples to wild theoretical possibilities. Here's what we know for absolute certain. Forward time travel is real. Time dilation is a proven fact. Every time you move, you time travel into the future by tiny amounts. Speed up enough or get close enough to a massive object, and you could time travel years, centuries, or millennia into the future. This isn't speculation, it's established physics, The only barrier is technology. We don't have the engines or energy sources needed to do it in any meaningful way. But it's not impossible. It's not forbidden by physics. Backward time travel? That's where things get murky. Maybe it's possible. Maybe it's not. Einstein's equations don't rule it out, but they don't make it easy either. Every theoretical method we've come up with requires things that might not exist: wormholes, exotic matter, cosmic strings, infinite cylinders. And even if those things exist, manipulating them would require technology so far beyond what we have that we can barely imagine it. Then there are the paradoxes. Maybe backward time travel is impossible because it creates logical contradictions that the universe won't allow. Maybe it's possible through parallel timelines where you don't actually change your own past. Maybe it works, but only in ways that are self-consistent. We don't know. What we can say is that time is far stranger than most people realize. It's not absolute. It's not the same for everyone. It's woven together with space into a single fabric that can be warped, stretched, and bent. In a very real sense, we're all moving through space-time, not just through space. And how we move through space affects how we move through time. The fact that we can even seriously discuss time travel, that we have mathematical frameworks and theories to describe it, shows how far physics has come. A little over a century ago, we thought time was absolute and universal. Now we know it's flexible and relative. Who knows what we'll discover in the next century? Maybe someone watching this video right now will be the one to crack the code. Maybe you'll be the one to figure out how to stabilize a wormhole, or how to harness exotic matter, or how to build the first practical time machine. Or maybe you'll prove definitively that certain kinds of time travel are impossible and explain why. Either way, the question of time travel sits at the intersection of everything we know about physics and everything we still don't understand. It pushes the boundaries of what's possible and makes us question the nature of reality itself. And that's what makes it one of the most fascinating topics in all of science.